Hello. Today we're going to be talking about the ideal gas law. So, the ideal gas law combines all four variables. So, we had our first three gas laws, which only had two variables. Then we had our combined gas law, which had three: pressure, volume, and temperature. But now we're going to combine pressure, volume, temperature, and moles. So, all four variables we talked about on the first day, all together in one equation. So it was discovered that if you take the pressure times the volume divided by the number of moles and the temperature in Kelvin, no matter how much of the gas you have, you're always going to get the same value when you plug it into this equation. And so that value is deemed R, which is the universal gas constant. And R is equal to 0.0821, and our units reflect this right here. It's liters times atmosphere divided by moles times Kelvin, or the pressure and volume unit on top and moles and temperature unit on bottom. So the gas constant's always going to be this number as long as we are using these units here. So R will always be the same unless you change the units. So R can be a different number only if you're changing. Normally it's the pressure unit that we're using. So if we're using atmospheres, it's going to be 0.0821. If we're using kilopascals, it's going to be 8.314. And these are the only two I'm going to have you guys use. They're the most common pressure units. But if we used a different pressure unit other than these two, we would have a different R value we would have to use. And so if we take this equation here and rearrange it so that everything's in the numerator, we get our ideal gas law, PV equals nRT, or PIVNERT, as I was taught to remember it. So we have pressure times volume equals number of moles times our gas constant times the temperature, and again, the temperature has to be in Kelvin. So you'll notice this is different from the previous gas laws we've talked about. All the other ones had a before on the left side and an after on the right side, right? A 1 and a 2 on the sides. However, this one, because it has all four of our variables together, we don't need to have a before and after to figure something out. If we know what pressure and volume our gas is taking up and the temperature, we can figure out how many moles of gas we have using this equation. So the thing is, you need three of the four variables in order for it to be useful, right? The R is always going to be the same number, it's a constant, but we need to have three out of the four of pressure, volume, moles, or temperature in order to find the last one. So I have a couple practice problems here. First one says, if I have 4 moles of a gas at a pressure of 5.6 atmospheres and a volume of 12 liters, what would the temperature be? So again, unlike the previous the previous questions we've been doing earlier this week, we don't have a before and after, but we do have moles, pressure, and volume. So we have 3 out of the 4 variables, so we can solve for temperature, the last one, using the ideal gas law. So our pressure is 5.6 atmospheres, our volume is 12 liters, number of moles, which again we represent with N, is 4.0 moles, and since we are using atmospheres as our pressure unit, we would use 0.0821 as our gas constant here. T, or temperature, is going to be our variable that we are solving for. Now we just plug them in. So again, we have P, or our pressure unit, times V, our volume unit, equals N, the number of moles, R, our gas constant, and T, which is our variable here. So we plug in the respective values into their respective spots. Then, to solve for T, we would get rid of the two terms that are being multiplied to T. So we divide both sides by 4 moles and 0.0821 liters atmospheres over moles Kelvin. So we end up with the left side on top and the right side in our denominator here. Then you just plug it into your calculator. You do 5.6 times 12 divided by 4 divided by 0.0821. And the reason the gas constant has all these weird units here is because if you actually take the time to cancel out the units, all of these units are going to cancel except for the Kelvin, which is the unit for our temperature unit here. So if we plug this in, we end up getting 204.6 Kelvin as our temperature for any gas that's acting ideally under these conditions here. So, second problem, I have a gas that occupies 12.0 liters at a pressure of 243 kilopascals, so we're using kPa here, a different pressure unit, and a temperature of 298 Kelvin. I want to know how many moles of gas I have in this container. So I have volume, I have pressure, I have temperature. I know what R is because it's a constant, it's always the same. So I can solve for N, or moles of gas. So we know our pressure is 243 kilopascals, our volume is 12 liters, our R value, since this should be kPa here. Our R value is 8.314, and then T is 298 Kelvin. So again, we have a different value because we're using kPa. I just forgot to change this unit, but that's why this is a different R value. So if we plug this in, pressure times volume equals, N is our variable, R, the gas constant, times T, our temperature in Kelvin, we get this equation. Now to solve for N, we just do a little bit of algebra. We would divide both sides by both of the terms here. We end up with N by itself equals the pressure times the volume in our numerator divided by our R value and our T value here. So once you have this, just plug it into your calculator and you end up getting 1.18 moles of gas are in this container. So in real life, this is one of the more useful gas laws and one of the more useful equations because we can measure most of these things using different gauges if we know how large the container is, so on and so forth. And we can then figure out something like how many moles of gas are in the container, or what's the pressure in the container if we put this much gas inside of it. So we don't need a before and after. We can just solve for any one of these variables given that we know the other three.